All right, so let's look at question 9, or at least part A of question 9 here. So one of the big ideas we're trying to build you up to in this module, in this section, is to compute derivatives, from their limit definition. So let's do that with this quadratic function here. So one thing I really want to emphasize is that, the derivative, one of the many ways we've talked about it, is it's an instantaneous rate of change. It's the slope of a tangent line. And it's not a coincidence that because we talk about the derivative being a slope, and the way you calculate the derivative is based on a slope calculation. So, you know, this is probably very close, if not identical, to what you've always, well, the way you've thought about slope for a very long time. So some change in y values divided by some change in x values. That's a rate of change, it's a slope. If we kind of turn that into, put that in function notation, what we have is this: f of x2 minus f of x1 over x2 minus x1. If we keep trying to compact this, maybe I don't want to look at two different x values. Maybe I just want to think about a single x value and look at what happens when, I start thinking about the distance between those x values. So from here, I'll say not f of x2, but f of just x plus h minus f of x. So whatever my x value is, since I can't calculate slope with only one point, I have to have this h that tells me how far away I can get, or what my distance of separation is between x and x plus h, and I'm dividing that by the change in x values, that's h. So really, these three things are different versions of the same information. I'm looking at the change in y divided by the change in x. So the way we get the derivative from this is when we think about what's going to happen to this what's going to happen to this expression as h gets really, really small and goes towards 0. So this is the limit definition of the derivative. And one thing I really want to emphasize here is that I have not done anything with the function in this question yet. And that's because this limit definition of a derivative it's generic. You can be applied to any function you want to deal with and any base point. So, and what I mean by base point is, so my function is x squared minus 3x. I don't want to find its derivative at any value of x. I want to find its derivative at simply a equals 2. So now we can put some specificity here. So if my f of x is x squared minus 3x, then what does that mean about f of x plus h? Well, what does it mean? For example, if I say f of 2, let's find f of 2 since we're going to have to eventually. If I want to find f of 2, that comes from me, everywhere I see an x, I input a 2. So 2 squared minus 3 times 2, that's 4 minus 6, or negative 2. Really is no different when you, instead of making my input 2 or any other number, now my input is x plus h. So this becomes x plus h squared minus 3 times x plus h. So now what I'm looking for is this. I want to find the derivative of f prime, at what value of x? I want to find the derivative at x equals 2. So now basically what I'm doing is I'm taking my generic limit definition, which is given by this thing that I've underlined, and I'm going to apply some details to it because I have a specific function and I have a specific value of x that I want to estimate, or not estimate. I'm going to find the exact derivative of this. So f prime of 2 is going to be equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. So there's one ingredient we haven't yet done. I'm actually going to just kind of replace x plus h with 2 plus h. Actually, I'll just go ahead and do that in the limit definition. So the limit as h approaches 0 of f of 2 plus h, which should be 2 plus h squared minus 3 times 2 plus h minus f of 2, which we said was negative 2 all over h. So basically, we're going to do some computation, do some algebraic manipulation, and see if this limit can be evaluated. So right now, this limit cannot be evaluated. If I simply plug in 0 for h, I get division by 0. That is not going to help me. So let's do some simplification and see what happens for us. What is 2 plus h squared? That should come out to be 4 plus 2h plus 2h plus h squared. Now distribute the 3 to the 2 and the h. So that's minus 6 minus 3h plus 2 all over h. Okay, so I don't see anything yet. I still can't evaluate the limit, so let's keep simplifying stuff. Let's combine some like terms. So I only have one h squared term, so h squared. What about all my h terms? I have 2h plus 2h minus 3h, so 4h minus 3h, so h squared plus h. What about all my constants? I have 4 minus 6 plus 2. So what does that come out to be? That just comes out to be 0. So I have h squared plus h all over h. So we still can't evaluate the limit, but we're getting to a place where we can. What's the limit as h approaches 0? In the numerator, I can factor out an h. So h times h plus 1 over h. Now this is what I've been waiting for. Now I can cancel out those h's and I have this. The limit as h approaches 0 of h plus 1. Now I can truly evaluate that limit. As h goes to 0, this goes to 0, this expression goes to 0 plus 1. So my derivative is 1. So this is not an estimate. This is not, an approximation. This is the exact value of this derivative. So this is going to take some practice to kind of get used to. I think there are 6 parts of this question. I would definitely try parts B and C if you want a little more practice with this, but hopefully this makes sense. And yeah, let me know if you have any questions.